here is the NMR spectrum of isopropyl butanoate. We are going to assign the peaks for the different hydrogens that we have in this compound. First, to begin with, we are going to find the number of hydrogens that is present in the compound and see whether it's going to match with what we have in the spectrum. So from the structure, we have got totally 14 hydrogens. And from the NMR spectrum, we can see that it is equivalent to a total of 14 hydrogens also. So we don't have to do any multiplication or do the math to find the number of hydrogens, right? So we already have got equal number of protons in the structure and as well as in the NMR spectrum. Now the next thing that we are going to do is we are going to go on to each proton and find the multiplicity of it. So this proton right here will be split as a triplet because it has got two neighboring hydrogens. And this one right here, we have to apply the Na plus 1, Nb plus 1 rule. So you have got three neighboring hydrogens. So that would be 3 plus 1. And then this would be 2 plus 1. So it will be split as total of 12 peaks. But you may not be seeing all these 12 peaks because there might be some overlapping of the peaks. Okay, so I'm going to just put this as multiplet. So this one is a multiplet. And let's go on to these hydrogens right here. It will again be split as a triplet because it also has got two neighboring hydrogens. Let's go on to the methane proton. The methane proton will be split as a septet because you have total of 6 hydrogens, 3 plus 3. That's going to be equivalent to 6 hydrogens. So applying the N plus 1 rule, 6 plus 1, that is equivalent to 7, which will be split as a septet. So this will be split as a septet. And then the methyl protons will be split as a doublet. So you have two methyl protons which are exactly in the same chemical environment, and both together will give us one peak, one signal. So this will be split as a doublet. Now, now that we have found the multiplicity, we are going to find where these protons are going to come in the HNMR spectrum. Let's focus on the methyl groups first. Now that we have identified the multiplicity, let's focus on the peaks to assign the different protons for it. First, let's focus on the methyl protons. There are two different types of methyl. So this is one type of methyl, and these two methyl groups right here is going to be the second type. So between these two, which one is going to be appearing in the d-shielded region? Obviously, these 6 protons right here are going to appear in the d-shielded region because they are closer to the electronegative oxygen. Whereas this one right here is going to be in the upfield region. Yes, in the upfield region, we do see a triplet, right? So this is going to correspond for A protons. So this peak right here, this triplet right here is going to correspond for the A protons. Since this is going to be split as a doublet, when you zoom up the spectrum, you can see the next peak is actually a doublet, which corresponds to a total of 6 hydrogens, and therefore we can easily assign this signal to be for the hydrogens that is present in the two methyl groups. So that would be our B protons. Now let's focus on the methylene hydrogens. Here we have two different types of methylene groups, and therefore two different types of methylene hydrogens, right? So because this methylene group is closer to the electron withdrawing substituent, and you have another methylene group which is one step away from it, right? Now between these two, obviously this is the one that's going to come in the field region, and this should be split as a multiplet. Yes, the next peak, the next signal is a multiplet, which corresponds to a total of 2 hydrogens. So this is going to be our C protons. And then the next CH2 will be split as a triplet, which corresponds to a total of 2 hydrogens, and therefore this is going to be our D protons. And then now we are left only with the E protons, which is a methane proton. Okay, the methane proton should be split as a septet, right? And you can see there is a peak here around 4.9 ppm, and when you zoom it up, this is what you're getting. So it has got total of 1, 2, 3, 4, 5, 6, 7 peaks within that signal. And this can definitely be assigned for the methane proton. So this is going to be the E proton. So this is the order that you will be going. First, try to match up the number of protons in the structure with the NMR spectrum, and then find the multiplicity, and then you can assign the peaks for the different protons.